Hello and welcome to yet another video of this course Signals and Systems. In the previous few videos we have been discussing about the linear time invariant systems. It's a special class of systems where we assume that the system is linear and it's also time invariant. So we did an analysis for the continuous time case where we expressed any arbitrary input in terms of the impulse function. Then we analyzed on that basis, applied the property of linearity and time invariance. Then we got a characterization of a continuous time LTI system, and it was in terms of its impulse response, right? And we expressed that as a convolution integral. Then we discussed some important properties of the LTI systems like causality and stability and how we can express those properties in terms of the impulse response. Now, in this video, we'll talk about discrete time LTS systems. And as far as analysis is concerned, you'll see there will be a lot of similarity between the analysis, the way we did it in continuous time LTS system. There will be a lot of similarity. Of course, the reservations that are for the discrete time case, they will apply that the signals which basically are used to define a system, they will be only defined for discrete intervals of time rather than for the entire continuous duration of the time. So for analysis, we'll start with, just like we started in the continuous time case, that any discrete time sequence say x of n, it can be expressed as in terms of the impulse response, in terms of the impulse function. Again, it's quite similar that we used in continuous time case. The only thing here will be, since we are discussing this for the discrete time case, the integral that will be replaced by a discrete summation that will sum up all the points, ideally from minus infinity to plus infinity, and like this, delta n minus k, right? If you compare it with the continuous time case, here we had an integral with respect to time, but since here the things are discrete, we have to use a discrete summation. Fine. Then again, we'll use the same notation. Let's assume that h of n, it is the response of a system. To be more specific, it is the response of a discrete time LTI system to a unit impulse signal. A sequence. In discrete time case, we prefer sequence over signal. So it is something like this, that h of n is the transformation on the signal, the sequence delta n. Then the response y of n of the same system, of a discrete LTI system, to some arbitrary signal x of n, it can be expressed as y of n is the same transformation t over x of n. Right. Then we can make this substitution that instead of x of n, we can write x of n in terms of the impulse function. So that's from k from minus infinity to plus infinity, x of k delta n minus k. Fine. Fine. Then we will apply the two properties. So first property is that since the system is linear, we can take the operator to t inside the summation, which means that y of n may as well be expressed as summation. K runs from minus infinity to plus infinity, x of k, and the operator t. Since you're assuming a linear behavior, it can be taken inside the summation. Right? Then again we can apply the time invariance property. Which means that if I have h of n transformation of delta n, then if I shift this input by some amount, say k, since the system is time invariant, that same amount of shift will appear in the output, right? So that this equation becomes our response of the system y of n. It will be summation k running from minus infinity to plus infinity, x of k, and this transformation, owing to this time invariance property, we can write as h of n minus k. Right? And this is basically the characterization of a discrete LTI system. Right? So this is again a convolution operation. So this is x of n convolved with h of n in terms of summation. This is the form. So this thing we call here that this is a convolution sum. In continuous time case, it was a convolution integral. If you see physically, the integral, it also integrates, it sums up, and sum is a normal sum. But the difference is that integral is a continuous thing. It is defined for a continuous domain, a continuous interval. Whereas sum, it is discrete. So you sum over some number of samples. You sum 5 samples, 6 samples, जितने भी samples पे आपका signal या आपका sequence define है. ठीक है? So for continuous time LTI system, we have a convolution integral. For discrete time LTI system, we have convolution sum. And both these quantities, both these operations, they include the impulse response. Right? So they are based on the impulse response of the system to that. Obviously, impulse response will be to the impulse signal. Right? So this is used. So let me put out here that convolution sum, like convolution integral, is used to characterize a discrete time LTI system. Right. Now it also has a similar properties that we had in the continuous time case. Right. So again, just for the sake of the completion, let's have a deeper look at this summation. So I have y of n is equivalent to, first we'll write it in the convolution form, and this is actually equivalent to k runs from minus infinity to plus infinity, x of k, h of n minus k. So if you see, it again involves some operations, some basic operations, physically speaking, right? So you have, again, the first thing, you have the folding operation, wherein the sequence h of k is folded and converted to h of minus k. Right? Then you perform the shifting, where you perform the shifting operation on h of minus k. It is shifted by some amount, say n units, and what you get is this h of minus k minus n. Fine. Where n can be positive and can be negative, and accordingly you can either shift the signal towards the right or you can shift the signal waveform towards the left. Then you perform the multiplication, where you multiply your input sequence x of k with this shifted sequence h of n minus k, and this multiplication is sample to sample. And let me write it here, sample to sample basis pay v multiply our two sequences. Fine. Then finally you perform this summation. Fine. So the products you get here, we sum of the, you can say, individual or partial products, and that summation will give you one sample value of y of n. Fine. And then you have to repeat the same process to get all the sample values of y of n. So you will see that mathematically speaking, it's kind of, I won't say it's complex, but it's involved. इसमें बहुत सारी computations आ जाती है. I'll take a simple example to illustrate my point here. Suppose we take a very simple example, a very simple case where I have the input sequence x of n. It is an explicit sequence which has been defined like this. It has 4 samples, each having a value of 1. Then also what is given is the impulse response h of n. Again, it is a small sequence of 2 samples. Both the samples have a value 2 and 2. Fine. So, and we need to compute y of n. So this is what we need to compute. X of n, h of n, convolution. Okay. So let's first plot. Just as has been our regular practice, we always try to get an insight into the physical meaning of the signal, and the best way to do is to plot it. So let me just go simple sequence here. It's not that complex. We can simply plot it. Fine. So I'll be naming it in terms of k, which is our dummy variable. So let this be our x of k, and this be our h of k. Now x of k has 4 samples defined at 4 points. At 0, then say at 1, 2, 3. Fine. And just to maintain the scalability, fine. So this is 0, 1, 2, 3. That is the 4 samples of x, each having a value of 1. And then h has 2, 0 and 1, each having a value of 2. Simple, so straightforward sequence. Now we are interested in computation of this y of n. So we'll write the summation form. So y of n, it will be summation k runs from minus infinity to plus infinity, x of k, h of n minus k. Right? So instead of, because these are finite sequences, this may be 4 elements, may say 2 elements. So we will try to compute this convolution mathematically rather than first folding, shifting, multiplications. Although वैसे भी आप कर सकते हैं graphically, but it will be, you have to plot a lot of graphs. So क्योंकि simple सा sequence है, we'll try to solve it mathematically using this summation. And summation is always easier to solve than integral. Right? So okay, let's do it sample by sample. Let's first compute y of 0. So y of 0 will be summation k runs from minus infinity to plus infinity, x of k, h of n ka value 0 hai, so it will be h of minus k. Now this is an infinite sum. So we will look at our signals kahan se defined hai. So they are basically defined from 0. Our x of k is defined from 0 to 3, and our h of k is defined from 0 to 1. So we'll take individual values, x of 0, h of 0, that's for k is equal to 0, because from minus infinity to minus 1 we don't have anything, so I'm neglecting that part. Similarly, then the second one will be immediately after this x of 1 into h of minus 1, that's for k is equal to 1, x of 1, h of minus 1. Then again the next one will be x of 2 and h of what you call minus 2. But you will see that it involves the term h of 0 जिसका वैल्यू हमारे पास है, h of minus 1, h of minus 2, और जो भी subsequent terms होंगी they will have the negative values of h because we have h of minus k, so they don't appear here, so we'll stop here. So x of 0 is 1, h of 0 is 2, so it's 1 into 2, x of 1 again it's 1, but h of minus 1 is 0. Similarly it will be like this. So what I get is simply 2, that is y of 0. Similar basis where we can compute the second sample. Let me change the color here. Y of 1, it again will be this infinite summation, k is equal to minus infinity to plus infinity, x of k, h of 1 minus k. इसी तरह I will expand this summation using these. This will give me an idea कि कहाँ से कहाँ तक मुझे expand करना है. Otherwise the sum exists from minus infinity to plus infinity. So it specifically depends upon your signal waveforms in question. So again let's start from okay, we will have x of 0, h of 1, the next one x of 1, h of 1 minus 1 will be 0. Then the next one will be x of 2, h of 1 minus 2 is minus 1. Again हमारे negative values आ रहे हैं h के, so we'll stop because we don't have negative values in h of in this waveform. So x of 0 again it's 1, h of 1 is 2, then x of 1 is 1, h of 0 is 2, then x of 2 is 1, but h of minus 1 is 0. So this will be equivalent to 4. Fine. So we have got y of 0, we have got y of 1. Similarly, you can get y of 2. Let me just quickly go through it. So let's compute y of 2 here. So y of 2 will be summation k runs from minus infinity to plus infinity, x of 2, h of 2 minus k. We'll expand it, so it will be x of 0 into h of 2 plus x of 1 into h of 1. Then we can also write x of 2, but x of 2 is okay, yeah, we'll just continue. So x of 0, h of 2, 2 for x of 1, then x of 2 into h of 0. Right? So x of 0 is 1, h of 2 is not defined, it is 0. X of 1 is 1, h of 1 is 2, x of 2 is 1, h of 0 is 2. So again this will be equivalent to 4. Right? So we have y of 0, y of 1, y of 2. Then likewise we will have y of 3, k is equal to minus infinity to plus infinity, x of k, h of 3 minus k. Again it will be x of 0 into h of 3 plus x of 1 into h of 2. Again x of इसके बाद x yeah, if you continue, x of 2, h of 1 plus x of 3 to 1 h of 0. So x of 0, h of 3, it will be 0 because we don't have h of 3. This thing again will be 0, this will be 2, and x of 3 h naught, this will again be 2, so it will be 4. Then you will compute y of 4, k is equal to minus infinity to plus infinity, x of k, h of 4 minus k. Okay, so again you will have x of 0, h of 4 plus x of 1, h of 3 plus x of 2, h of 2 plus x of 3, sorry, 0 1, okay, it's fine, 4 3 2, h of 1 plus x of 4, h of 0. This will be 0 because h of 4 is 0. This will again be 0. This will again be 0. This will be 2 because x of 3 has a value of 1. H of 1 has a value of 2. And then x of 4 is not defined. We have only up to 3. So this will again be 0. So we'll totally get 2. Then again, if you compute y of phi using the same summation, you will see it just turns out to be 0. तो जो आपका signal आएगा y of n, it will have sample values. So 0 पे 2 आ रहा है, then 4, then again 4, then another 4, then 2. This will be your y of n. Fine. So if you plot it, if I plot it here, so this is y of n. So it has y of 0 पे, it has a value of 2. So let's suppose, let's scale it down. This is 2. Then y of 1 पे, it has a value of 4, 4. Then another 4, 4, 4. Then again 4, 2 and 0. 4, 2 and 0. Okay. So this actually is 2, this is 4. Right? So this will be our output. So we'll further analyze it in the next video.